Right, let's just start. So can you guys hear my voice?
Yes, Professor.
Okay, good. Hold on. Let's see. Right, today we're gonna talk about resonance circuit. Okay, so as you guys know, resonance circuit is one of the most unique characteristic circuit in the RF application. Okay, let's see. So this is a basic structure of the series RLC network. As you guys understand, if there exists L and C together with R, this system is actually second order system in terms of S domain. Okay, so however, when we talk about the resonance circuit in terms of RF application, what we are interested in is just omega domain, okay, not S domain, which means we just convert S into J omega. Okay, so for this simple RS network, right, G is given by J omega L plus 1 over J omega C plus R, right? So if you just rearrange those in terms of real and imaginary, right, you can get this expression. As can be seen over here, right? If omega is chosen such a way that this value becomes 0, okay, then omega is just a square root of LC, right? Then imaginary part becomes 0, and what you get is R, okay? So in this regard, if you express this in terms of complex diagram, it is this, right? So at resonance frequency, the energy stored at L equals energy stored at C, okay? So at omega 0, right? So energy, stored energy over here is this, right? The stored energy over here is this, right? So it becomes the same, okay? So for this, situation, let's just define the quality factor. Whenever you talk about resonance circuit, you have to understand the meaning of a quality factor, right? The fundamental meaning of a quality factor is given by this, which is just energy stored energy divided by stored divided by the energy loss per second. Loss per second means this is a power loss, right? Power line, because of power multiplied by dt. You just take integration, then this is energy loss, right? So here, this is a power loss per one period of time, right? So if you multiply it by power loss, then it's energy loss, right? So this is a energy loss 2 pi multiplied by stored energy divided by energy loss. Okay, that's what it means. So as I mentioned before, at resonance frequency, Wm, which is the stored energy in the magnetic field, equals the stored energy in electric field. So, at resonance frequency, you may just express something like this. Or, okay, either of them are fine. So in this regard, let's express those in terms of RLC and IMV. Then, double M is given by, I square L, right? Here, if you just choose a peak, right, then this becomes this, right? Therefore, it is a 1 pulse I square peak multiplied by L, right? That's why you get 1 pulse over here, okay? So, and also P loss is just caused by the resistor, okay? So in this regard, the loss caused by resistor is I square R, right? The reason why we express those in terms of I is that we are talking about series network, which means current is same for all the components. That's why we want to express all of them in terms of I, right? So therefore, Q is omega 0, and this is 1/2 of I square R. This is 2 multiplied by 1 pulse of I square L, right? So just cancel out, right? Cancel out. So what is left is omega 0 L divided by R. This is Q. So as I said before, omega 0 is a square root of 1 over square root of LC. So if you put this together, right, then what you get is R, and this is actually, square root of L divided by C, which is actually G naught. So you may just express G naught over R. This is another form of Q, okay? So another way of, expressing this is since omega 0 L omega 0 L is same with omega 0 C, right? Because this is the condition for resonance, okay? So we substitute this into here, then this becomes omega C R1, right? That's why we get this, okay? So let's take a look at, the component voltage when we express this component voltage in terms of quality factor Q, okay? So this is very straightforward. For example, this voltage drop over inductor is VL. VL is J omega 0 L I, right? At resonance, right? At resonance, I is just Vs divided by R, right? So if you put this together, then VL is J omega 0 L divided by R Vs, okay? What is this? This is Q. So VL is plus J Q Vs, okay? Which means, if you apply Vs, then voltage drop over this, inductor is Q times over applied voltage, okay? then you can easily get this is a minus QVS, right? Because VC is what? J omega 0C 1 I. As I said before, I is just Vs divided by R, right? Therefore, this is a J omega J, and this is a Q Vs. So this is a Q Vs, right? This is a minus J Q Vs, okay? Which is exactly same magnitude with the opposite polarity. Okay? That makes sense, right? Because once this is resonate, then this all of them become 0. Then Vs is just applied to over here. Okay. All right. So if you draw G as a function of omega, right, then you can easily see that it's looking like this. Okay. So this is omega 0. When omega is smaller than omega 0, right, which means you know, capacitor is dominate. Therefore, as the frequency goes up, impedance is getting lower and lower because of this. Okay. However, if omega is higher than omega 0, then it's looking like inductive. As the frequency goes higher, impedance goes up like this. Okay. This is a main characteristic of a series RS network. Here it becomes R. Okay. Right. So then where can I use this voltage gain in RFIC? You know, basically you can apply this directly to here, right? This is CGS, okay? You have a RS, okay? You have a VS, right? So let's say if you just want to make it, you know, resonance, right? Then this is looking like RS, right? This has to be RS, shown to be RS, right? So the network is just looking like this. Again, you know, again, so C is minus JQ VS. Here, Q is what? 2R omega L or 2 omega RC, right? In this case, because you have R here, right? Okay. So what you get is at this V in is what? V in is you know, minus JQVS. Okay. So ID is what? ID is something like this. GM multiplied by Q in VGS. Okay. Therefore, you get this amount of improvement in terms of voltage. Okay. All right. As I said before, let me request one of you guys to explain this to peer student. Okay. So, Bampu, can you explain this? Can you explain what I mentioned up until now here? Okay.
So I propose
You just briefly mentioned. Okay, let me ask you, okay?
yes.
When it is a, let's consider series RS network. when omega 0 equals 1 over square root of LC,
Yes, Professor.
what is the stored energy distribution between L and C?
It's equally, Professor.
Equal, right? Okay.
Professor.
Right. So let's talk about Q, right? So when it is a resonate, right? So at inductor, what is the voltage drop when it is a series network?
It's
We apply Vs, and what is a voltage drop over the inductance?
this is a half of Vs.
No. As can be seen here, right? If you apply Vs, right, the voltage drop over inductor is just a Q times Vs. If
Yeah, sorry.
set Q equal 100, then this be, let's say this is 1 volt. If Q is 100, this is 100. Then what is a voltage drop between here and here? What is the voltage between? What is the voltage VAB? What is this value? June, what is this value?
Yes, Professor. Zero.
Okay, this is 0, right? Okay, good work. Because you have a plus J QVS, but you also have a minus J QVS, right? So voltage between this and this becomes, okay? That's why you get V out equal Vs at resonance. Make sense, Banfu?
Yes, Professor.
Okay. So therefore, Fu, so how can we get the advantage of resonance in the MOSFET design, MOSFET-based amplifier design? It's something like this, right?
Yes, Professor.
What is a Q over here? What is a Q?
The first one, Professor.
This one. This has to be, effectively, this has to be RS, right?
Just
Okay.
R.
So Q is, what is a Q?
Just omega L over L.
Which one? Omega L over what? For this one. For this one. What is Q?
RS L's omega
Sunyok, what is this for this network? What is Q for this network, Sunyok? 순혁이 답이 없어. 안 들려?
아니,
그럼 보고 하면 되잖아. 응? 이거. 이게
오메가.
그,
네.
그지? 그지? Okay. So let's talk about the quality factor of the parallel RS network. Okay. So when it comes to parallel RS network, what you have to use is Y parameters, right? Because this is a more straightforward way. Right? Just J omega C plus J omega L plus 1 over R, right? So this is G, okay? So we can express Y in terms of this, okay? In the same way, right? So as we've seen, as we observed, right? IC is J omega C V0, right? At resonance, right? What happened to V? V0 is just IS divided by Y. This is G, so which is just a G IS, okay? Therefore, it becomes J omega 0 C, and this becomes a G, right? So here, as you can see, this is omega 0 C over Z, okay? Which is exactly, you know, if I just put Y equals Z plus JB, this is imaginary of Y. This is a real of Y, right? This is a definition of Q. So real value of Y is C. Imaginary of Y is J omega C, okay? Omega C. So this is a Q, okay? So for this current becomes amplified by JQ, okay? How about this? This is amplified by the minus JQIS. Therefore, the total current here and here is just compensated. So total current just conducted to here. Okay, exactly same. So based on those, you guys can see, you know, the impedance as a function of omega is given by this one. This is a capacitive and this is inductive, right? Inductive. In opposite way, this is a inductive and this is a capacitive for parallel network. You notice that the bandwidth is just 1 over Q. So here you can just prove with this. Okay. So as can be seen, Z is R plus J, omega L minus plus J omega C. So if you take out J omega R plus J omega L, J omega like this, you just take out J omega L, okay? There is J omega L, then this is a 1, and this is a minus omega square. This is a C, and this is a L, and this is a 1. So when omega is a square root of LC, then this becomes 1 and becomes 0. So if I express this, right? So R plus J, and this is a omega, and L1 minus. Okay, so if I express this in terms of deviation, right? If I express, let's say omega into omega 0 plus delta omega, right? Then I can approximate like this way here, right? So R plus J, and you just take out omega 0, which is actually, square root of LC, right? So just by just take out omega 0, and this is 1 plus omega 0 delta omega, right? Just put this to here, okay? Put this to here, and rearrange this, and you can get this, okay? So this is again, Q0 is what? Q0 is omega L divided by R. Okay, so you just cancel out R, and you have omega 0. Omega 0 cancel out with this. So what you have is L. Okay, so this is L, and you have a delta omega, right? So G in is R plus J, 2J L delta omega. Okay, so let's define bandwidth as the frequency where impedance becomes just a square root of R, right? Then this is just R divided by 0.707. Okay, so here this is the frequency where if you just take a scale, then this is a twice of R scale. Okay, so the twice of R scale, and using this relation, you can see bandwidth is 1 over Q0, and therefore this is what Q0 is actually delta omega and omega 0. Yeah, omega 0 delta, omega 0 delta. Right. So this bandwidth is a fractional bandwidth. Okay, this fractional bandwidth is 1 over Q0. In the same way, for the parallel network, you can also express it exactly the same way. Okay, so the fractional bandwidth is 1 over Q0. So now let's talk about the resonance circuit for the short-circuited lambda over 2 transmission line. Okay, this is one of the most widely used resonator designed with a transmission line. Okay, this transmission line is easy to implement, right? You just design like this, make it short, and choose this as a lambda over 2. Then what happens? At this point, right, your voltage should be always 0, right? Since this is lambda over 2, so your voltage must be here 0. This is 0, right? You may also, get another mode of resonance, right? When n is 2, you may have this. You also may have this, right? Whatever it is, if each edge has a voltage equal to 0, then it is resonate. Therefore, for the series resonate network, right? This is a you know, let's say this is omega 0, and this is a 2 omega 0, 3 omega 0, blah blah omega 0. It is repeating. Okay, so let's calculate the input impedance using well-known equation. Okay, so G in equals G naught and GL and plus G naught tangent hyperbolic gamma L G0 plus GL tangent hyperbolic gamma L. Here gamma L is alpha plus J beta L. Okay, so in this case, right, beta is what? Beta is lambda over 2 multiplied by L is 2 pi lambda over 2, right? L is lambda over 2. Okay, so it becomes pi. Beta L is pi. Okay, when beta L is pi, what happened? Tangent hyperbolic wise, right? It becomes 0. Right? So this is 0. And what you get is G in and G naught and GL. And you also have this is 0. You also have this tangent hyperbolic. This is actually, what is that? Okay, so you have to use this way. Okay, let me just since GL is 0, right? GL is 0. You have to use this first. G0 and GL plus tangent hyperbolic gamma L. G naught GL tangent hyperbolic gamma L. So here GL is 0, right? So this becomes 0. This becomes 0. So eventually this cancels. So which means this is G naught tangent hyperbolic gamma L. Okay, this is what you get. So here gamma is what? Alpha plus J beta. Okay, so you put over here, then from the equivalence, you can express like this. Okay, so we can assume that alpha L is very small. So tangent alpha L is just alpha L approximately. So we just substitute this to alpha L. And we also need to consider perturbation. So we said omega 0 is omega 0 plus delta omegas, right? As we've done before. So here, beta L is just omega L divided by Vp. So here, instead of omega, we just put omega 0 plus delta omega. Then we can express like this. So throughout this expression, you can express G in terms of G naught plus J blah blah. So this is R plus J X, right? So as we've seen before, right? The series network is just expressed in the bandwidth, this is expressed J2 L delta omega, right? So from this line, if you compare this to this, then R is G naught alpha L. L is you just compare this and this. G naught pi divided by 2 omega 0, right? So then L is just from the definition of resonance, you can get this. Okay. Therefore, if you just, since this is a series resonance circuit, which is repeating like this over the frequency. Okay, so quality factor Q is omega L divided by R, and if you put this R and this R over here, then Q is just a beta divided by 2 alpha. Okay, all right, you have this quality factor. This is also very intuitive. This is very intuitive. I will show later. Okay. So let's talk about short-circuited lambda over 4 transmission line, which is exactly speak, which is a parallel resonance circuit. Okay, so once you just make this circuit whose wavelength, whose length is lambda of 4, then this is looking like a parallel network. We can do exactly the same way, right? Since GL is 0, you get this this expression, and this is exactly the same with what you've done, right? The only difference is when you calculate this, right? So here L is lambda of 4 instead of lambda of 2. So once you put this over there, then this is omega 0 나누기 VP. Then as you can see, VP is what? Actually lambda divided by T, which is 2 pi, and this is what? Omega divided by beta. Okay, so VP is omega divided by beta. Okay, so here beta is this omega divided by beta, omega divided by VP. So beta is what? Pi divided by lambda, and you have lambda divided by 4. Then this is pi divided by 2. Okay, so this. With this observation, you can express a cosine beta L equal to like this. So if you put them together, then it is exactly parallel network. Okay, so with this condition, R is G naught divided by alpha L, which is 1 of G. C is pi divided by 4 omega 0 G naught. Right? And if you put them together, then you still get quality factor is expressed by beta divided by 2 alpha. Okay. Same. Okay. Mingyun?
Yes, Professor.
Okay, so if you want to implement a parallel resonator with a short circuit, then what is the required length of the transmission line?
Lambda over 4.
Yeah, okay.
Professor.
If you want to implement a short circuit series resonator, what is the required length of the short circuit transmission line?
람다 오버 2, Professor.
Okay. So if you implement lambda short circuit with lambda wavelengths, okay, is it parallel resonator or series resonator? Again, if you want to implement the short circuited lambda wavelengths, lambda length transmission line, is it series network or parallel network? And what is the, and also second question is, what is the resonance frequency of them? The lowest resonance frequency. Can anyone answer this question? 한국말로 돼, 한국말로. You guys may speak in English, speak in Korean. If you are fine. Okay, my question is, what if I implement short circuit lambda transmission line? Is it parallel network or parallel resonator or series resonator? You guys understand what I try to mention? Okay, you guys understand what I try to mention?
네, 네.
This is very funny, right? You just assume that, let's say you want to implement a resonance circuit at 10 gigahertz. Okay. Then lambda is what? Lambda is 3 centimeter, 0.03 meter. Okay. So I just design based on what I learned. Okay. Let's say this is a lambda over 2. So I designed in such a way that this is a 1.5 centimeter and made it short. Okay. What I expect is this is a short circuit with a lambda over 2 transmission line. So this must be series resonator. At 10 gigahertz, right? That's true. However, this must be parallel resonate at 5 gigahertz. You understand? At 5 gigahertz, what is lambda? It's a 0.06, right? 0.06 meter. What is a lambda for? 1.5 centimeters. Okay. If I make a short circuit lambda of 4, right? This is exactly what happened at 5 gigahertz. Okay, so let's go back to my question. What if I make a short circuit with a lambda? Is it short or open? This is a short circuit at lambda line. For any short circuit, lambda over 2 short circuit line. this is a lambda, this is a short circuit, this is a series network. Just, this is all, if you just set lambda equal this, you will get series network. Right? If you have a lambda of 4, right? Lambda of 4 and n is odd, then you have a parallel network. Okay, understand? That's why this is this line. Therefore, this is a series network. But this can be also parallel network with a different frequency. For example, this is operating at 10 gigahertz, right? Half of lambda is what? 5 gigahertz. This must be also resonate. But at 2.5 gigahertz, this is looking like a parallel resonant network. Parallel resonant. Understand? 이해했냐? 어? 그래서 이걸 만들 때 있잖아. Therefore, when you design any series or parallel resonator, you also need to consider the harmonics as well. Otherwise, it may cause lots of trouble. But in different way, if you implement a circuit using this characteristic, then you can easily, remove, even or odd harmonics using such a simple way of, filtering. Okay. 이거 태훈아 이거 남다 우리 했잖아, 그지?
네, 했습니다. 네.
저기 어디서 썼냐 이거?
그 클래스 F에서.
스위치에서 썼잖아, 스위치에서.
네네, 맞습니다. 네네.
우리 과제에 스위치에서 썼잖아.
네, 스위치에서. 네네, 맞습니다. 네.
왜
제가,
하나도 안 본 것처럼 다들 그래 맨날 쓰는데. 근데 이거 만들 때 여러분들 조심해야 돼. 조심도 하지만 여러분들이 오더 하모닉이나 이븐 하모닉을 줄일 때 이런 식으로 패러럴 레조네이터나 시리즈 레조네이터를 잘 만들면 아주 쉽게 여러 개를 잘 제거를 할 수 있어. That's why I put this in, in the class slide. Now let's talk about loaded and unloaded quality factor. Right? So unloaded quality factor Q is without any loading effect caused by external circuit. Okay? Loaded Q is a quality factor with the external load resistor RL. Therefore, it is always lower than Q0. Okay, so the external Q is defined by omega 0 divided by omega 0 L divided by RL, where RL is a load resistor. This is external resistor. Okay, then this is a very straightforward line. Why? Because Q total is R total divided by omega 0 L. Here R total is R loss plus R load. Right? So if you just express this, right, this is omega 0 L and R loss plus omega 0 L R load. So this is unloaded Q, right? This is what? This is external Q. Therefore, loaded Q is this relation. Okay, very straightforward. Then why do we need to separate external external Q, is it convenient? Why is it convenient? Because typically R loss is not well controlled. This is not well controlled. Okay, so with this relation line, we know require the QL from the bandwidth or any other thing, right? Then we also know, the load resistor. Then we can determine the value of loss, R loss, from this relation. That's why we use this. Make sense? Okay. Mingyun, can you explain what I mentioned before? Why do we need to use the external Q? 한국말로 해.
저항에 대한 로스는 조절하기 힘들어서 이제 필요한 밴드위스 큐팩터에 따라서 레저넌트 서킷을 먼저 정해지면 이제 그에 따라서
그렇지. require 때는 로스를 우리가 할 수 있는 거지, 그지?
네, 맞습니다.
잘했어요. Okay. So there are many aspects of Q factors. Okay. As we observe the line, Q factor means 2 pi times the ratio of total energy stored divided by the energy lost in single cycle. Right. Okay. This is the first definition from physics guys. Right. Physically, it's something like this. Okay, which is expressed like this. Okay. Equivalently, Q factor is what? This is a 1 over fractional bandwidth, right? This is delta omega divided by omega 0, which is 1 over fractional bandwidth. Oh. Okay. Equivalently, Q factor is approximately the number of oscillations required for a freely oscillating system's energy to fall off the 0.2% of each original energy, or the voltage or current falls off to approximately 4% of each original amplitude. Okay. With this, using this observation, right, you can easily get Q factor. Okay. This is an example. This is the voltage of a second order system, RLC network, right? So this RLC network has this kind of, time transient result with a damping factor less than 1. This is an underdamping line. With the underdamping, it will oscillate. So there are several number of oscillations, right? You just count. Okay. So there exists a ring down method. Okay. The ring down method is like this way. So we just make it resonance. Okay, like this way, and you just using this observation line, so it falls to 2 to minus 2 pi. Okay, so just take a ln, and this is a minus 2 pi, and so you just count how many cycles you take to halve the amplitude. So this is a half amplitude. Right? So using this observation, Q is just a pi divided by ln 2 from this. So this becomes half. Okay. then just take a ln. This is ln 2q omega t, and this is ln 2. Okay, so here you just count number, right? So this omega t, this t is just nt. Then this omega is what? T over 2 pi. So you cancel. So 2 pi n. Okay, so this is pi n divided by q. Okay, this is ln e, cancel, right? Pi n divided by q equal ln 2. Okay, so n is what? N is what? Pi. I'm sorry. Q is what? Q is ln 2 pi n. Okay, that's why you get this. So if you calculate this, pi divided by ln 2, it is 4.53. Therefore, you can count number and multiply it by 4.53, then you get approximate number of Q. For this example, up until half, you have a 6 number of oscillation, 6 number of cycle, right? So this is 6 multiplied by 4. This is around 4.5. This is around something like this. Right? 27, right? 27. Okay? Understand? 이해했지? Okay, so this is a ring down method. So you just don't know how to, measure Q from the oscillation, right? Just a 4.5 divided by ln 2 multiplied by n, right? And as we observed, right? So based on the series and parallel network, quality factor is exactly 1 over fractional bandwidth. Okay, this is fine. For the second order system, right? Second order system, which is typically expressed by like this line. Right? This is second order system, right? For this second order system, right? So what is the pole point of this? This is a P minus A, EA minus P plus minus square root of B square minus 4AC, right? So since it has 2, so this is A minus P plus minus AC, right? Okay, you put this together over here, okay? Then you get the solution. You have a pole pair, right? You have 2 pole pairs, okay? So for this second order system, Q is defined by 1 over 2 damping factor, okay? So since damping factor omega 0 is defined as alpha, okay? So Q is just if you express this Q in terms of alpha, then this damping factor is just alpha divided by omega 0. Therefore, this is 2 alpha omega 0, okay? So this is this omega 0 is a natural frequency of oscillation, right? So here, alpha is okay. Alpha is what? Alpha is actually for RC network, right? RC network is for the RC network, alpha is RC. Okay, so this is exactly 1 over tau. Okay, so you get this result. All right, this is actually widely used definition for the second order system. Okay. So basically, whenever we talk about quality factor Q, we are talking about loss. So we need to understand the loss mechanism of a typically integrated circuit. Okay, so this is this represents the several loss mechanism that can be happen in the integrated circuit. Okay, so the first one we can think about is substrate loss. Okay, this substrate loss is caused by mainly two current. One is eddy current, which is magnetically induced current. Second one is displacement current, which is electrically induced current. Okay, the third one, that is just direct current conduction in the lossy medium. So ohmic, eddy, and displacement current. All of them are just considered as a substrate loss. Second one is if you just place tap, right, for the bias, for biasing, or to make a reverse bias, right? Let's say you make a center tap, right? Then there must be definitely, because this is a typically ground, AC ground, right? So there must be current pass nearby this. Therefore, there exists a lateral current, which is causing ohming loss as well. Also, for the transmission line, the current is crowded at the edge. This edge current is crowded at the edge. Okay, due to skin effect, right? So the R is just the R scale multiplied by L and width, right? Here R scale is given by sigma and skin depth, 1 over skin depth, right? Okay. Kevin, do you remember the expression of the expression for the skin depth? What is the equation for the skin depth?
Yes, Professor.
What is that?
Square root of
1 over square root.
1 over square root. 2 over omega.
Oh, okay, that's fine. Okay.
Yeah. And
Omega.
mu and conductivity.
Okay, good. This is just a square root of pi f mu sigma, right? So what is the approximate value of this if the conductor is a good conductor whose sigma is around 10 to the minus 10 to the 7 Siemens per meter. Let's say sigma is around 10 to the 7 Siemens per meter. What is the skin depth at 10 gigahertz? Just to say approximately, that's fine. It's approximately less than 1 micrometer.
Yeah.
Right? Yeah, you
Yes.
remember, right? Okay. Good. So it also has a magnetically and electrically coupling. Okay, so this cat. And also there exists, radiation because of, the change of velocity. Okay, so mainly say the loss mechanism consists of radiation and loss caused by the screen effect, loss caused by substrate, current, which consists of ohmic current, eddy current, and displacement. Okay. So this is actually what I forgot last time. Let's just I just presented for your information. Okay. From the definition of quality factor, right? So any dielectric material with a tangent, loss tangent is given by this. That's what I mentioned. Now, how? This is a very straightforward actually. So there are two ways of proving this is true. The first way, which is widely used in material guys community, is given by this definition. QD is omega, energy stored divided by P loss, right? So here, energy stored is twice of electrically stored energy. Okay, so basically, epsilon consists of epsilon pi plus j epsilon 2 pi, actually minus. Okay, minus j epsilon 2 pi. Okay, so here, stored energy is from epsilon pi. Okay, so the power loss is actually sigma E square. Okay, so here sigma is modeled from epsilon 2 prime by this way. Omega, sigma is omega epsilon 2 prime, which is exactly same. Right, so you can easily, prove this. How? J is actually J conductivity plus displacement current J omega epsilon E. Okay, so this is a sigma E, right? So you just say sigma plus J omega epsilon E, right? In the same way, if you just represent J in terms of displacement current, J omega epsilon prime minus J epsilon 2 prime E, right? If you compare these two, you can see that sigma is just omega 2 prime. Okay, so this is converted to this. So then this cancels. What is left is just epsilon prime over epsilon 2 prime, which is exactly 1 over tangent, loss tangent. Okay, so this is one way. Second way is this. Okay, when electromagnetic wave propagates through the lossy dielectric medium, right? Gamma is defined like this way. Gamma is actually defined as a J beta, which is actually omega square root of mu epsilon. Okay, so here we put epsilon prime minus J 2 prime instead of epsilon. Then we rearrange this from the Taylor series. Okay, then we can easily get this. The first one is beta, the second one is alpha. From what you observed, right, quality factor Q is a loss, energy loss, and energy stored, right? Energy stored, which is just K beta divided by 2 alpha. So basically the energy, electric field is propagating like this way, E2 minus J alpha and E2 minus J beta Z, not alpha. Okay. So from this observation, from the resonance circuit, QD of the transmission line is a beta divided by 2 beta, 12. So we put this, then you get this. Okay, that's why we can conclude that whatever it is, the quality factor of any dielectric material is just 1 over loss tangent. Make sense? Okay, now let's talk about series shunt transformation. Okay, so at fixed frequency, this is important. At fixed frequency, okay, at fixed frequency, one can convert between series network and parallel network. Okay, even though you convert between each other, if a frequency is different, this is wrong. Okay, so at the same frequency, RP is given by this. Okay, RP is RS 1 plus Q square, which means since Q is always larger than 0, right? Therefore, RP is always larger than RS. Okay? If Q is larger than 1, then RP is just approximately Q square over RS, which is very large. Different from the real value, the imaginary value is almost the same because this is XS 1 plus X inverse square. Okay. So be notice that the Q from this is XS divided by RS. The Q from this parallel network is what? B divided by C, right? Both are same. If you put this, then you can easily, prove it. Okay, this is a derivation of a series of parallel conversion, which is a very, very straightforward, so I don't need to talk about it. Right? You just make it equal and just compare each other, then you can get this. Okay, now let's talk about maximum power transfer condition. So for the transmission line theory, right, the solution is given by this voltage equal to blah blah. Then I can just from the definition of G naught is defined by V0 minus V I0 or minus V0 minus I0 minus. Okay, so which means for me to express current in terms of voltage, incident and reflected voltage can be given by this one. So if I divide the first one by second one, right? V divided by I at G equals 0 is GL, right? So from this relation, I can calculate the gamma like this. Okay. So here, the average power delivered to the load is input power multiplied by 1 minus gamma L square. Okay. So the average power is this. This is incident power. Therefore, we conclude that we need to make a gamma equals 0 to deliver the largest power to load. So we need to make this 0. In order for us to make it 0, GL has to be G naught, which is called as impedance matching. In other words, if you derive this more rigorously for the case with a G naught equal to complex number, then you can see gamma is given by this. Therefore, in order for us to make a gamma equal to 0, you have to choose GL equal to G naught conjugate. Okay, this is a conjugate matching. Okay, that's why we need to achieve the conjugate matching. Dogan, why do we need to achieve a conjugate matching?
uh, to maximum the power delivery.
Okay, good. All right, so this is previously we investigate the case with a transmission line. Okay, so now let's talk about the maximum power transfer in terms of circuit. Okay, so again, the power delivered to the load, any load, is given by this line. So I square RMS and real value of load. Right? This is the effective power delivered to the load line. Okay, so here, real value of GL is RL line. And I is what? I is VS divided by RS plus GL, right? So if you take a scale, then it's looking like this one. So here, I rearrange by setting GS equal to RS plus JXS and CL equal to RL plus JXL, right? We just rearrange them, then you get this. So to achieve maximum power delivery, this is a very straightforward line. We can naturally choose XS equal to minus XL so that this denominator becomes 0. This is the smallest. If this make it 0, then this become high, right? This is the easiest way of choosing. Now, what is RL then make this largest? This is very straightforward, right? So we get this, then we rearrange this in terms of we just expand this like this. Then for the optimum RL, we just take a derivative with respect to RL, right? Then what we can get is RL equal to RS, right? So this is a typical way of extracting the min-max value, right? So because this is a this shape, so if you choose this here and the denominator become minimized, which means this become maximized. Okay, so we conclude that RL has to be RS and XS has to be minus XL, which means XL has to be XS conjugate. Okay, that's why you get this. Okay, this is the proof based on the circuit theory. All right, let's take a look at the impedance matching. For an optimum power transfer, right, we observe that the impedance conjugated impedance matching is required. Right? Let's say G in is matched to RS and G out is matched to RL. Okay, and also we assume that matching network itself has no loss. Okay. If the matching network loss is 0 with this condition, this perfect match condition, you can easily relate input power equal output power. So what is input power? This is a Vin, and you have a RS as a load. So Pin is just a Vin square divided by RS. Right? In the same way, R out is P out is what? PL divided by V out, right? Square. So this is equals, make this equal. Then you can easily get V in square divided by RS equal V out square divided by RL, which means V out divided by V in equals square root of RL divided by RS. Okay. So in conclusion, if you achieve a matching between input and output, okay, if you implement a matching network, right, the impedance resistance transformation ratio is actually voltage gain. That's what it means. Okay. The same way, if you express this in terms of current, you can also get similar observation. The ratio is just the inverse of current gain. Okay. That's why once you achieve impedance matching, you can achieve a better gain, like what we observed, the resonance circuit at the input. Okay, that's why. All right, then how can we implement a matching network? This is very, very straightforward, right? As we observed, right? So we can easily convert between series and parallel network. Once I convert the series network to parallel network, then you can scale up and down by Q square, right? So with this relation, R parallel equals R series multiplied by 1 plus Q square. So R series R parallel minus 1 square root is quality factor Q. This is a required Q of the matching network. Okay. So here, R parallel is always larger than R series. So we just put the larger one here, smaller one here. Okay. That's very straightforward, right? Then once you determine Q, since Q is just X divided by R of the series, or XP divided by BP divided by GP, right? So you can get this. So with this, you can calculate you can synthesize error. So this is an example, okay? So I want to convert, right, GRL to RS. Here RL is 10. Let's say RS is 5, 50, okay? So in this case, RS is larger than RL, right? Since RS is larger than RL, I need to put series network with RL to increase impedance. In this case, I put inductor. So once I have this, then I may just convert it into parallel network. And this is L prime. This is RP prime, which is 1 plus Q square. Then how can I get this value? Quality factor Q is R parallel 50 divided by 10, right, minus 1, which is 2, right? So quality factor equal 2. So RP is RL multiplied by this, right? So RL is 10 and 1 plus Q square, this is 5, then it's a 50 ohm, right? Parallel network, this is a 50 ohm. So the last thing is to resonate out this with the C. Okay, what is L prime? L prime is omega L. This is XL. Is what? XP is X series 1 plus Q inverse square. Since Q is 2, right? So this is 1.25. 1.25 XS equal XP. Okay. Then I can get XP. So from XP, I can synthesize 1 over omega C. Then you can get C. Okay. Very straightforward. So now let's talk about the insertion loss of any passive network. When we synthesize the matching network, the insertion loss is given by this. Okay, insertion loss is from the definition. Insertion loss is PL divided by P in. Here P in is power delivered to the load plus dissipated power. This is total input power, right? So if I rearrange with respect to RL, which is a power delivered to the load, then I can write like this. Here, Q is proportional to stored energy divided by power loss. Right? So therefore, Q dissipated, P dissipated is proportional to Q component. P delivered to the load is proportional to 1 over network, synthesized network. Therefore, P dissipated by PL is what? QC, QNet. Right? That's why you get this. Which means, in order for us to reduce the insertion loss, first we need to use a component with a high Q. Second, you need to reduce network quality factor. Right? This is the only way to improve to reduce insertion loss. Just make this large. Make this large, then this becomes small. Right? So if component quality factor Q is much larger than network quality factor, then this becomes 0. So we have a 0 insertion loss. Okay. So that's why we need to use good component with a high quality factor. Or just use a small Q network. Now let's talk about Smith chart. You guys are very familiar with them. So I'm gonna skip this. Okay. So for your, as you guys understand, right? As you understand, right? So if you just use a transmission line, and let's say this is load, and let's say this is a length of L. The impedance seen at this is, let's say if I say this is gamma, right? Gamma doesn't change with respect to length, but gamma is just gamma E2 minus J beta L and 2, right? 2. Because of this, right? Because of this. You know, if you move by length of L, then you have a theta equal to minus 2 beta L. Okay. Therefore, this is the way it goes. So beta is 2 pi divided by lambda L. Okay. So if I choose L equal to 0.5 length of wavelength, then what is 2 beta L? This is 2 by 2 pi lambda and this line. So this is a 2 pi, which means if this is length equal to lambda of 2, then it rotates by 2 pi. Okay. So any load impedance can be expressed on top of a Smith chart. This is very familiar with you guys, right? So if you draw, you know, constant VSWR circle, then the VSWR circle can be looking like this. Okay. So this is a L matching network. Very straightforward, right? We already did it before. So for this example, this is a 10, this is a 50 ohm. There are two ways, right? The first one is move to this direction, right? So just add a series, this means a series, right? This trajectory is a series, and this is a positive. So positive means, J positive means this is inductor. So we need to, this is a 10 ohm, we need to add a series inductor, okay? Series inductor, like this. And next, go down, which is a capacitor. But with this Y Smith chart trajectory, this is a susceptance. So this is following this. Okay, very straightforward. Now, this is just for your information, because as a RF engineer, right, we are actually not much familiar or interested in the, you know, time transition. Okay, the transient simulation or transient analysis is actually out of our scope. Okay, we are not interested in the transient time, except for power amplifier design. For power amplifier design, definitely we need to do it, because power amplifier analysis, it is a highly nonlinear system, and that's why designing power amplifier is somehow difficult for RF engineer. Okay, that's why you guys need to understand what's going on. All right. So here I compared the body plot versus pole zero diagram. Right? This pole zero diagram is widely used to make an analysis of you know, time transient time domain time domain analysis, right? So as you remember, right, the second order system is given by this line. So if I get root of this line, this is pole, then I have two poles, right? Two poles, which is given by minus omega n plus minus omega n square root to 1 minus this line. That's why you have here and here. Okay, this is typical pole zero diagram of the second order system. So for the second order system, you typically express like this way, right? Here, this omega n is actually alpha, and this is actually q is actually 2 this line. So you just may express like this, okay? So from the pole zero diagram line, if both poles are aligned like this, right, then this is overdamped. There is no oscillation at all. Okay, overdamping means damping factor is larger than 1. Okay, for the second one, right, this has a pole pair like this, then it is underdamped. So since this is a damping factor less than 1, it has a oscillation, something like this. Okay, if it has a same root, you just say it is critically damped. Okay, so based on the position of the pole, you can just estimate the transient response of the system. Okay, so again, you can just real and from the real and imaginary value, right? This is omega, and this is alpha or sigma, right? This is sigma. Okay, so you express like this one. So for second order system, this is a plus omega n and 1 minus this one. This is a minus omega n 1 minus this. Okay, so this is a damping factor omega n, which is alpha. Alpha is a sigma. Real value is sigma. This is alpha. Okay, this is sigma is alpha. Here alpha. Okay. Here, this is alpha. Okay. So this omega d is as we already observed, omega d is omega n square root of minus zeta square, and this amount is natural frequency. Okay, so you just if you just make a synthesizer with respect to this, then you will see this is omega. So for with this second order system, right, you can easily see, you can differentiate, the type of filter. For example, if the transfer function is looking like this with the omega n scale, which is typically looking like this line. This is a low pass filter line, low pass filter. Okay. In the same way, band pass filter is expressed like this way. The denominator are all the same. Okay, band pass omega n divided by qn, qs. Okay, notch s square plus omega n square, high pass s square. Okay, so this notch is just notch is like this, right? This is a low pass plus a high pass, low pass plus high pass, low pass plus high pass. Okay, right. So the damping alpha, as we've seen, zeta omega n, right, which is just zeta is 2 zeta, right? 2 zeta is actually, zeta is 1 over 2q. So this is given like this. Omega n divided by 2q, okay? So this is exactly same with the transmission line, right? So you observe q is what? Beta divided by 2 alpha. For the time system, right? Time system. I mean time-based system. Q is what? Omega n divided by 2 alpha. Beta is you know, the proportional ratio which convert length to theta. This is a proportionality component which convert time to theta. Okay, so same. So damping factor is just BF divided by 2, which is, since this damping factor is 1 over 2Q. So all of them, as you can see, is expressed in terms of quality factor Q, which is a fractional bandwidth. So here RS, right? That's what we observed before, right? So you can also express the G naught divided by R, or R divided by G naught, right? From omega L divided by R, right? So here we put omega equal to square root of LC, then you can get this. Okay, so why do we do this? Because we want to get the impulse response in time domain, right? So the impulse response, the difference between the impulse response and step response is that the impulse response or the impulse response, right? Input is impulse, right? Delta, and step response input is step function. So the resulting step response is actually the integration of impulse response, like this. Okay. Reversely, if you know step response, you just take a derivative with respect to time, then you can get the impulse response. Okay. So the second order system here, we put the perturbation function as a delta, which is impulse. Okay. Then using Laplace transformation, you can easily get those equations. Okay. Underdamping, undamped, underdamped, critical damp, overdamp. Okay, so you can get this. Step response is the same. Here, this is a unit. So you get those results. So if you draw all of them, right? So for example, undamped, this is just a sinusoidal, right? If it is underdamped, you have a gradually reducing oscillation signal, right? And critically damped, you have this one, right? And overdamped, you have a more fastly settled. Okay. So for the unit function, right? But ideally it has to be like this. So for the undamped, input is something like this, starting point. If this is underdamped, it's something this. It is critically damped, it's something like this. It's overdamped, it's more gradually settled. Okay. So this is a typical RLC series network. So LRC, right? So just a very simple calculus. Okay. So as a result, right, this is exactly, same shape for low pass filter, right? Omega 0 square. For your information, high pass filter, right? You have a same denominator but numerator S square. For the notch, you have a S square plus omega 0 square, right? For the bandpass, you have a omega n divided by q, because this defines the bandwidth and S at the numerator, right? That's it. So you have a two solution. One is here plus, the other is minus, right? So you have a two solution. So if you draw, the pole point position is here, right? So if you change, damping factor, right? This is underdamped. This is underdamped. And when damping factor is 1, this is critically damped, right? So critically damped is something like this. Underdamped, you have a gradually reduced oscillation. Okay. So here is the lab 7. So design a microstrip with a Z0 equal 50 ohm in 65 nanometer CMOS and 40 nanometer CMOS. Extract the Z0 and gamma at 10 and 150 giga, 220 giga using short circuit lambda 4 transmission. Okay. So as you observed, right, you can just express G in. Right? Once you take out S parameter, right? So basically, this is a lambda 4 short circuit. This is a parallel network. So you just make an analysis in terms of this, right? So this value is R, right? R, okay. So with the bandwidth, you can get Q, right? Then, this R is expressed in terms of G0, right? We already have seen this, right? Relation R is G0, a function of G0 and alpha, right? Yeah. G in, we extract this by using S parameter, right? So this is exactly 1 over R plus 2J delta omega C, right? So here you can RLC from this. So from R, which is this, right? This is R, right? You can get alpha, okay? Where can I get the beta? You just, once you get alpha and R, alpha and G0, beta is just my beta L is just a theta, right? Once you know theta from the S parameter, S21, right? Then beta is very straightforward, right? Then you can get gamma and G0. Okay. We will see what's going on after taking this class, after taking this home. Okay. Also design, extract the G0 and gamma using ABCD parameter from two-port network. Okay. There are two ways. Do the same way. Do the same thing for CPW and GCPW. Okay. Due is 2 weeks later. Okay. Any question? 질문 없어? 없어요? 자, 그럼 끝낼게. 수고들 했어요.
네, 교수님. 감사합니다.